Okay, guys, we're going to carry on with chapter 13.5 and we're going to look at example 13.6. Okay, so perhaps you can follow in your textbook as well. Because it's a photocopy, I messed up a bit of the edge over there. But basically, we've got these racing cars that are going around a circular track. Okay, perhaps you've never seen it. I decided to just go and take some pictures off the internet. There's a circular track. Okay, this is circa 1922. So thank you for that. These cars are going around a circular track. Can you see that it's got a banking angle? Okay, there's an angle there that they go in a circular track. So the track is circular. Okay, they're riding in this the circular track or oval track or whatever, and they're riding at an angle. Okay, the question is why is there that angle? Okay, I guess that's part of the question. Here's some more examples. Here's some bunch of cars going again it's a circular track, but can you see that there's this angle? There's an angle there. They're riding at an angle. Here's a nice close-up of a car that's on a circular track going at some angle theta here. Okay. So what is that, and why is it banked? Why is there a banking angle? Okay. So there it is. And the question is, determine the banking angle for the racetrack so that what? So why? So that the wheels of the racing cars will not have to depend upon friction. Okay. So first of all, we need to know what is a banking angle. Perhaps why would we want a banking angle? And what has this got to do with friction? I guess that's really the answer. So what is this banking angle? So that the cars do not have to depend upon friction to prevent the car from sliding up or down the track. Okay. So let me just start here with this picture over here. So you can see this car, there's no banking angle here. Can you see that? It's just a flat road, and this car is going around a bend. So we've got curvilinear motion. Okay. Now, as this car is going around the bend, what is the only force in general that is keeping it from sliding out as it's going around the bend? What is that force? It is friction. Okay? Friction. So there's a friction force on these wheels as this car is going around the bend. The friction force on the wheels is stopping the car from sliding out. Okay, so there's a force inward. Okay? Now, what do you suppose? So the point is, we want to get this car going in a curve. And so if we've got it flat, if the road is flat, then the only force that is pushing the car inward is friction. Now, what happens if we increase this angle? So now it's not going on a flat road, a flat surface. It is going at an angle. But what do we want to do? We want to get the car to go around the curve. So just in general, without going into any details, can you see that if we increase this angle from 0, then the normal force, there's a normal force here, right? So we have the friction force, and then there's a normal force. That normal force would now begin to contribute to pushing the car inwards. Okay? So that's the basic idea here. I mean, I haven't gotten into this in much detail, but this is just like a 5-minute consideration of how to describe this problem. So the question is, why would we want to bank the road to increase this angle? Because this normal force then, okay, this one here, we had the normal force over there, and we had friction here. And friction was the only component that was pushing you inwards, right? Stopping you from sliding out. But now, if we increase this angle, we bank it, okay, just like this, then we've got friction plus plus this normal. Well, actually, what we're doing is we are reducing friction, right? Because the friction component will begin to reduce and the normal component will begin to increase. Okay, so hopefully that gives you just a basic idea of what is happening. So when we come to this question, it's saying, what is this banking angle so that we do not have to depend on friction? So as we increase this angle at a certain velocity, what's actually going to happen is that we're going to get to a point where we do not need friction to stop us from sliding out or from sliding down. Okay? All right. So I hope that kind of helps you understand this thing. You can go and research it more and so that you kind of understand this, okay? So number one, so now we're going to try to solve what this angle is. It's a curvilinear motion problem. And as I said before, in kinetics, when we're, chapter 13, when we're dealing with curvilinear motion, we're going to look at our normal, tangential, and binormal coordinate system, okay? So if we look at this from the top, we can see that this is the racing track from the top, right? We're looking at it from the top, from the binormal direction, okay? And at any point, we know that's our normal direction, that's our tangential direction, and the binormal is coming out of the page. But I just want you to take note here. Come on, man, focus. I don't know why this is not focusing. Well, I'll tell you why, because it's a cell phone, that's why. Okay, assume the cars have negligible size, a mass m, and travel around the curve with radius rho and a constant speed v, okay? So, can you see that the cars are traveling like this? That's your tangential direction. There's your normal direction, and your binormal is out of the page. And it says a constant speed v. So what is our acceleration in the tangential going to be? It's going to be 0, right? Okay. But now the way that we analyze this is we're going to look at the car face on. That means that up is the binormal direction, and the normal direction is towards the center of curvature. And because we have constant speed v and our acceleration in the tangential is 0, all we're going to look at is the normal and the binormal directions, okay? So there's our coordinate system, normal and binormal. And then what do? The next step is our free body diagram. What do we have with our free body diagram? We've got weight going straight down, and we've got our normal force here, right? Okay? The important thing is this. It says, what should the banking angle be so that we do not have to depend upon friction? So what we're saying is that at a certain velocity and a certain angle, we will not have to depend upon friction to keep us going up, to prevent us from sliding up or down the track. So the assumption is that there's no friction. At a certain angle, there's no friction, which is stopping us from going up or down. Okay, so do you notice here in the free body diagram, there's no friction here. There's just the weight and the normal force. Okay, so then we break everything up into its normal direction and into the binormal. Some of the forces in the normal is mass times acceleration in the normal. We have the normal force, sine, it's that component there. That's what we have there, and it's in the positive normal direction, equals mass times acceleration in the normal. But what is the acceleration in the normal? It is v squared over rho. Acceleration in the normal is v squared over rho. So we've got this equals mv squared over rho. Okay, equation 1. Now, let's look at the binormal direction. The sum of the forces is in the binormal is 0, right? Recall that. When we're talking about normal tangential binormal coordinate system, we assume that motion in the binormal direction is 0. There's no acceleration in the binormal direction. Okay? So what's happening there? Normal cos theta, right? minus mg. Those are my forces. My forces in the binormal direction. Normal cos theta minus mg equals 0. Okay, so we got two equations here. Then we solve. Remember, we're trying to solve for theta. Okay, we're trying to solve for theta. Work this out, and you're going to get tan theta is v squared over g times rho, and your angle is now equal to this arctan v squared over g rho. So now what does this mean? What does this mean, guys? I really ask you to think about this critically. I'll spend maybe just a minute on it because I don't want to make these videos too long. What it's saying is this, that if I want to drive on a racetrack with a certain angle and not depend on friction to keep me from going up or down the track, then I need an angle which is equal to the arctan of v squared over g times rho. Okay? So it would help you to basically look at this. Theta depending. So what we see as theta is a function of velocity, and it's a function of the curve, the radius. Okay? And what I would suggest you do, just to go and check it out, is plot this curve, theta versus velocity and theta versus radius. So plug a range of velocities into here and plot this curve, and plot a bunch of velocities and get the angle. Plot a bunch of radii and get this angle. Okay, so I quickly paused the video and I went and did this quickly in Excel. So what you see is theta as a function of velocity. I only did it for velocity. You can go and try this for the radius rho. But as you see, here's a plot. As I increase my velocity, my banking angle, can you see that it keeps increasing and increasing? So what does that mean? It means that at zero velocity, okay, I'm on my banking angle is 0. Remember, there's your banking angle. So at zero velocity, my banking angle is 0, which makes sense, right? I don't need any friction to keep me going from side to side. But as my velocity increases, I'm able to increase this banking angle, and the car can keep going at that specific velocity without requiring friction to keep it from going up and down. And can you see that as my velocity goes to much higher speeds, say even to 10 meters per second, then then we can even get up to this high angle there. Okay, so I hope that helps. Cheers, guys.